video. This is related to the Boolean laws and its proofs. In the previous video, we have seen that what are the different Boolean laws and theorems, why it is necessary, what is the significance of the Boolean laws. Now in this video, we'll see that how we can prove these Boolean laws. So let's start with the first one, that is a plus 1 equal to 1. We have to prove it that a plus 1 equal to 1. Because you will see that we are using this thing, a plus 1 is equal to 1. Not only a, anything plus 1 will equal to 1. So let us see how we can prove it. So I am starting with the left hand side, that is a plus 1. So a plus 1, you can write, see, anything a plus 1 can be written as a plus 1 into 1, because a plus 1 into 1 equal to a plus 1 only. So we are writing a plus 1 into 1, and we also know that a number plus complement of its number is equal to 1. So what I am doing here, I am just replacing this one with this a plus a bar. See, this is the same thing that you are getting here. Now after this thing, you will just open the brackets. A into a plus a into 1 plus a bar into a plus a bar into 1. Now we will use other laws, that is a into a equal to a. In the generalized form, we can say that if you are multiplying two identical numbers, it will be equal to the net number only. X into x will equal to x. It will not be x square. Okay, always keep in your mind. Now, a plus a is a. So, a is there. A into 1 is a. A is there. A into a bar equal to 0. A plus a bar equal to 1 and a into a bar is 0. So, 0 here. And a bar into 1 is a bar. Now, plus 0 is same thing. Now, a plus a. We all know that a plus a equal to a. A into a equal to a. So, I am using that property of Boolean algebra. A plus a equal to a. So, here it is a only. And a bar as such. And at last, again we all know that a plus a bar equal to 1. That's why it is equal to 1. So this is the first law, that is a plus 1 equal to 1. So we have to play smart here, that we are just taking a plus 1 into 1. Okay, and then use the other Boolean algebraic laws and prove it. So after that, the next is prove that complement of 0 is 1. It is very easy. I am just taking this 0, and 0 can be written as 0 bar plus 0. Just like a bar plus a. And 0 bar equal to 1, that's why, hence it is proved. Okay, so the third is prove that idempotency law equal to a plus a equal to a. Now we are using this thing a plus a equal to a. Now we have to prove this thing that a plus a is equal to a. So how will you proceed? The same thing here. I am starting with the left hand side, that is a plus a. It can be written as a plus a into 1. Again, 1 can be written as a plus a bar. So this is, in an extended version, we can write it as a plus a into a plus a bar. Okay, you can see at the second row here, a plus a into a plus a bar. Now a plus a is a only. So it is equal to a into. Now a plus a bar is 1. So it is equal to 1. So that's why it is equal to a. So in such a manner, we have proved that a plus a equal to a. Okay. So let's move further. Next is this annulment law, that is a double bar equal to a. Now we will prove it a double bar equal to a. So again, I'm just starting with the LHS, that is A double bar. You can take plus 0 because anything plus 0 equal to the same thing, same number. And you can write 0 as A into A bar. So A double bar plus A bar. See this thing. Then using the Boolean algebraic laws, we can write it as A double bar plus A into A double bar plus A bar. After that, this thing A double bar plus A, because this thing is equal to 1. Understand this thing, that as we know that A plus A bar equal to 1. Now I am taking not A but I am taking A bar as a number. So a number plus its complement. Its complement is, because A bar is the original number, so its complement will be A double bar. It should be equal to 1. The same thing is repeating here also. A double bar plus A bar equal to 1. That's why we have written it that A double bar plus A into 1. Now, again, we know that 1 is A plus A bar. Okay, so you can write it as A double bar plus A into A plus A bar. Now, I am just changing the sequence. A plus A double bar into A plus A bar. Now, you can write it as A plus A double bar into A bar. This is known as a distributive property that we have already seen in the initial videos. And that is equal to 0 because, see, A into A bar equal to 0. Now, in place of A, I am taking a number A bar. So, it is A bar into A double bar should be equal to 0. So, that's why it is equal to 0. Now, A plus 0 is A. That's why it is A. So, this is the annulment law. So, the main laws or main properties that you have used in this Boolean algebraic laws are, I am just summarizing here, it is 1 plus A or A plus 1, it is equal to 1. Anything plus 1 equal to 1. Next is A into 1. A into 1 is A. A into A equal to A. A into A will be A, will not be equal to A square. Now, A plus A equal to A. A plus A equal to A. It is not equal to 2A. Next is A plus A bar equal to 1. A into A bar equal to 0. In the similar manner, you can write A bar plus A double bar equal to 1 and A bar into A double bar equal to 0. Okay, so using these important properties, you can prove any Boolean laws or theorems. Let's move to the other part. Next is prove the absorption law. A plus AB equal to A. Now the question is, you are having A plus AB equal to A. So A plus AB, as left hand side shows that A plus AB. So you are just taking out the A common here. It is A 1 plus B. And as we have seen that 1 plus something equal to 1. So here 1 plus B equal to 1 only. So it will be A into 1, which is equal to A, hence proved. This is the law number 5 here, absorption law. Let's move to the next part, that is degenerate reflection law. So what is degenerate reflection law? It says that A plus A bar B is equal to A plus B. A plus A bar B is equal to A plus B. We have to prove it. Whenever we have to prove something, we have to take the left hand side. We have to prove it equal to RHS, or you can take the right hand side. You will prove it to the left hand side. Here we will take the left hand side here. that is a plus a bar b. Now we are having a plus a bar b with us. A plus a bar b. So a plus a bar b, you can write it as a plus a bar into a plus b. After that, we all know that a plus a bar is equal to 1. So it is equal to 1 into a plus b, and 1 into a plus b is equal to a plus b. Okay. So this is how we have proved that degenerate reflection law. Yeah. Let's move to the new part. New theorem is distributive property. We were using the distributive property. Now we will prove how the distributive property is equal to the other side. That is a into b plus c is equal to ab plus ac, or you can say a plus bc equal to a plus b into a plus c. You can see here that this property a plus a bar, we have used this distributive property only. Okay, so a plus bc can be written as a plus b into a plus c. Here also a plus a bar into a plus b. Now we will prove it. Okay, so I am taking with the right hand side here. A plus b into a plus c. What is expected here? Expectation is just open the brackets. So whenever you will open the brackets, it will be a into a plus a into c plus b into a plus b into c. Okay, so it is a into a is a only. We all know that a into a means sum. If I say that x into x will be equal to x. Okay, actually we are taking just a as a generalized form. Otherwise also b into b will be b, c into c will be c. Any number into that number equal to the same number. So a plus a is a, then a into c plus b into a plus b into c. So into a into a is a. I have written here a. AC, as such AC here, AB and BC. After that, now we are just taking out the common terms here. So A 1 plus C plus AB plus BC. We know that 1 plus something equal to 1 only. So 1 plus C equal to 1. So A into 1 plus C is 1. A into 1, A plus AB plus BC. Now we will take A out of these two terms, A plus AB. So A plus AB will be A into 1 plus B. Same here, that 1 plus B will be equal to 1 only, just like 1 plus C equal to 1. The same thing here also applies, that 1 plus B equal to 1. So 1 plus B is 1. It is A plus BC plus BC. This is what is required here. So A plus BC we ever require. This is how we can prove this distributive property of the Boolean algebra. Let's move to the next part. The next is Con-Census Theorem. First of all, understand what is the Con-Census Theorem here. Con-Census Theorem is a theorem of Boolean algebra. What does it say? It says, see, AB plus A bar C plus BC equal to AB plus A bar C. It is also known as redundancy theorem. So it is AB plus A bar C plus BC equal to AB plus A bar C. So you can see here that the consensus or resolvent of terms AB and A bar C is BC. So it is a conjunction of all the unique literals. Now we have to prove it. So the three variables are present. First of all, how we will move forward, we will check that how many terms are present, how many variables are present. Okay, you can see that in the consensus or redundant theorem, there are three terms and it is having the three variables a, b, c. So three variables must present in the expression. So here a, b and c are used as the variables. Okay, and each variable is repeated twice. You can see here a 2 times a and a bar, b 2 times b b, c 2 times c c. Okay, and one variable must present in complemented form. Okay, these are the conditions for applying the consensus theorem. Understand this thing, that consensus theorem or redundant theorem says that it can be applied to those terms if there are three terms and each variable is repeated twice. Means if there are a, b, c, then a should be 2 times, b should be 2 times, and c should be 2 times in these terms. One variable must present in the complemented form. Means that out of a, b or c, there should be either a bar, b bar or c bar in the terms. Then we will move forward. So here we have seen that all the initial conditions are fulfilled. Now we are going to solve this consensus theorem. Here three variables are there. One is in the complemented form and all the variables are in the duplicacy mode. Okay, so let's prove it. So it is AB plus A bar C plus BC. Okay, let's start with AB plus A bar C plus BC. So first of all, what you will do, you can write it as AB, A bar C, BC, because in BC there is no A. What I did, I have seen that AB has A bar C has A, either in A or A bar term, but BC does not have any kind of A. So I can simply write it as 1 into BC, because 1 into BC is BC only. Now, because A term is missing, so we are just writing 1 as A plus A bar. Okay, A plus A bar. We have just written 1 as A plus A bar, and now open the brackets. AB plus A bar C plus ABC plus A bar BC. Now after that, we have just rearranged it. You can see AB, now this ABC term here, ABC plus A bar C plus A bar CB, just rearrange the terms. Now again, because you can see the C here, C, but C is not present in the first term. So it is AB into 1. So it is AB into 1 plus ABC plus A bar C plus A bar CB. So now what you can do, you can write it as AB into 1 plus C, because 1 plus C equal to 1. Anything plus 1 equal to the 1. Okay, so I can write it as 1. You can expand 1 as 1 plus C. 1 can be written as 1 plus B, 1 plus A, 1 plus C, anything, because here C term is missing. That's why we are writing AB into 1 plus C plus A bar C into 1 plus B. Because we have just taken out the common terms A bar C here. Now 1 plus C is 1 only, and A bar C into 1 only. So it is AB plus A bar C. So I'm just repeating the things, that consensus theorem can be applied if three conditions are fulfilled. Which are those three conditions? Number 1, three variables. Number 2, all the variables in the duplicacy mode. Number 3, one variable in the complemented form. After that, we have just started with the left hand term, and because in term of BC, A is missing, so we can write it as A plus A bar into BC. Then just open the brackets, because AB plus ABC, you can take AB common. Okay, so it is 1 plus C. Similarly, here you have taken the common terms out. After that, you have proved it. So this is how we can prove the consensus theorem. Now let's take one more example here. Example is any circuit can be given and okay, simplify this circuit. Then you can simplify it using the Boolean algebraic law or the simple same question, or a function can be given to you. See, let's take a question that it is a circuit. For example, this is A, this is B, okay, and we have put a AND gate here, and then again a OR gate there. See, this is C, and this OR gate has two inputs, one is B and other one is C. And this C is also fed to the AND gate also, and this B is also fed to a AND gate also. Okay, and this is having a further AND gate, and output of this plus output of this is OR gate. This is, for example, Q. Now you have to write a Boolean expression of this circuit. For the Boolean expression of the circuit, first of all you have to solve it. So because it is an AND gate, A and B are the inputs. So AB here, it is OR is B plus C here. Now again AND is there, so it is BC. Now this is again an AND gate, so AND gate is multiplication, so it is BC into B plus C. Now at last we have to solve it because it is a OR gate here. So OR gate is having the two inputs, one is AB and second is BC plus B bar B plus C. So your Q can be written as AB plus BC B plus C. Okay, this is the expression. Now the question says that simplify this expression using Boolean algebraic laws. Question is simplify using Boolean algebra. Okay, means now we have to use some Boolean laws and theorems to minimize it or to optimize it. Now we are having Q equal to AB plus BC into B plus C. So you can open it. First of all, let's open it. AB plus BCB plus BCC. Okay, which is equal to AB plus BC plus BC. Why I have written AB plus BC plus BC? Because here you can see that BCB. So B into B will be B and C into C will be C. So the same thing I have applied over here. So it is AB plus BC plus BC. Now you will use the law of Boolean algebra, that is A plus A equal to A. So it will be equal to AB plus BC. Or you can write it as B into A plus C. Simple thing is B A plus C means you will, let's draw the circuit diagram for the same. So you will take a A, you will take a C, put a OR gate here. For example, it is A, it is C. Okay, now I want with a AND with a B. So I am just taking a wire that is for your B and put a AND gate here. Okay, so this is your B. And at last this is Q. So you can see that this circuit is very simple as compared to circuit number 1. For example, this is circuit number 1 and this is the circuit number 2. You can very well estimate that how simpler it is. Circuit 2 is very simple. Okay, and it is having only 2 logic gates instead of 1, 2, 3, 4, 5. Here 5 logic gates are there. But in this case, only a single logic gate is. Two logic gates are there. One is OR and one is AND. So you can better estimate that if the components are less, if the logic gates are less, it means that the operating speed is very much higher. Less delay time will be there. Okay, less delay time is from input signal transition to the output signal transition. There will be fast in speed because less logic gates are there, so it will be fast, and less power consumption is there. Less power consumption, so less cost is there, and it will have a great reliability. So that's why Boolean algebra is necessary. I have shown you using a circuit example that why Boolean algebra is important, because otherwise you will go with this thing that Q equal to AB plus BC into B plus C. You have to use many logic gates here, but you can see that it is a very simpler function, that is B into A plus C, just using the Boolean algebraic laws. This is the benefit of the use of Boolean algebra. And now I hope that you understand that why we are going towards the VLSI. So VLSI is very large scale integration where we are optimizing the circuits. We are just minimizing the circuits. Why? Because if the circuit is less complex, means if a circuit is very simple, it will take a very small space. It will take a very less power. It should be cheaper. It should be fast. That is the requirement of the today's era. So that's it about this particular video. In the next video, we will see the further part of the Boolean algebra. Thank you so much. Have a great day ahead.